Hi guys, this is Nitin John Raj, roll number 201501246. This is my science report. The topics to be covered in this report are the Hermite polynomials, Laguerre polynomials, the moment of inertia matrix, and rocket propulsion using Hamiltonian and Lagrangian dynamics. Now, before we dive into these topics, let's just consider the following scenario. Let's take a point mass m, which is connected to a spring of constant k. Now here we know the kinetic energy is p squared by 2m, where p is the momentum and m is the mass. And the potential energy is equal to kx squared by 2, where x is the displacement from the mean position. Okay? From this we can get the Hamiltonian, which is equal to k plus u. And with a little algebraic manipulation, where we take omega is equal to root of k by m, we arrive at this. Now let's take the operators. Let's multiply by psi and take operators rather than the actual variables. So this is the Hamiltonian operator, the momentum operator, and the displacement operator. We're pretty familiar with these. Now the momentum operator is given by minus IH dou by dou x, and the square of that is this. And basically when you simplify this expression, we end up over here, where the Hamiltonian operator on psi is equal to this expression. Now in this expression, h is the reduced Planck's constant, m is mass, c is just a constant, x is the displacement, and omega is the angular frequency. Let's take the equation Hamiltonian operator psi is equal to E psi. That way we can get the eigenvalues. But if we were to get an eigenvalue which is independent of x, basically an eigenvalue which is a solution for all values of x, then all coefficients of x, the sum of the coefficients of x, must be equal to 0. Therefore we get this equation, which simplifies to this, and we get a value for our constant c. And when we substitute this in our initial equation, we end up here. And this gives us energy in the ground state, which is h omega by 2. Now let's apply Hermite polynomials to this. Hermite polynomials, there are two definitions. One is used by physicists, one is used by probabilists. We're only going to concern ourselves with the physicist definition. Okay, so this is the generating function of the Hermite polynomial. When we differentiate this with respect to t, we end up getting this recurrence relation. Alright, that's pretty cool. Let's move on and differentiate with respect to x. We end up getting this one. And when we combine the two, we end up getting the second derivative of hn minus 2x, first derivative of hn, plus 2n hn is equal to 0. This is Hermite's equation. Now, let's just rescale this equation. Let's take a function such that this is the definition of the function. And we end up getting another form of Hermite's equation, which is this. Okay, now let's again look at our energy equation, our Schrödinger's equation, as we saw in the quantum oscillator. This is what we had with a little algebraic shuffling there. And if we look carefully, this is nothing but another, well, it's the same. They're similar equations, and therefore we can write this in terms of this. And when we do that, we end up getting this equation, and we can solve this to get the wave function to be equal to this. So we found the wave function in terms of the Hermite polynomial. That's pretty cool. Okay, and using this, we can take it a couple of steps further. We can say that 2me by h squared by a squared is equal to 1 plus 2n, and therefore get an equation for our energy at every single state, h omega n plus half. And this is in accordance with the ground state energy which we got over here. Thus, the Hermite polynomials have helped us find the wave function of a quantum harmonic oscillator. Alright, there's some additional information on Hermite polynomials here. I'm not going to go into that right now. Let's move on to the Laguerre polynomials. Now, this is the generating function of the Laguerre polynomials, and when we solve it, we end up getting this equation, the Laguerre equation. That is x second derivative of ln minus 1 minus x into the first derivative of ln plus n ln is equal to 0. Now, the Laguerre polynomials will help us find the energy states of an electron revolving around a hydrogen atom. So let's consider an electron in a hydrogen atom. The Schrodinger equation, as we know, is this. That is minus h squared by 2m del squared psi plus u into psi is equal to E into psi. Now, if we break psi into its three variables, we get this. And solving for this, we end up finally getting, well, we get over here, okay? And here, chi is basically just a refactoring of r. Rho is equal to alpha r. Well, you can read this up. Now we need to introduce another concept with Laguerre polynomials. Now, it's known that the kth derivative of ln is equal to minus 1 to the power of n, kth derivative of ln plus k. That's a pretty interesting result, and this helps us obtain the associated Laguerre equation, which is x into the kth derivative. Well, this is it. Now, the solutions of using this, we can get chi of rho is equal to this. And so we found chi in terms of the Laguerre polynomial. And if we fix lambda in this equation to be n, an integer n, we can quantize the energy states as usual, as is very common in quantum mechanics, and we end up getting this value. That is minus e squared by 4 pi epsilon naught to a naught n squared. And now a naught here is the Bohr radius. Thus, from that we can get psi is equal to this, where n of nlm is basically a normalization constant. You can find the normalization constant by solving this equation. And at the end, we end up with this equation. So we found the wave function for an atom in the for an electron in the hydrogen atom. Also, a fun fact, the Laguerre polynomial are related to the physicist version of the Hermite polynomial. This is the relation. You can look into that later. Now let's talk about the moment of inertia matrix. Now we all know what the moment of inertia is. It's just a rotational analog of mass with respect to the equations of force and motion. Now, this is basically the definition of moment of inertia for a rigid body. Okay? Here we have the moment of inertia matrix. And each of these terms, they're defined over here. Ixx is basically the moment of inertia around x-axis, around y-axis, around z-axis, product of x and y, product of y and z, product of z and x. It's pretty elementary. So now let's consider IPR is equal to lambda r. We're doing this so that we can find the eigenvalues of this. The three eigenvalues which we obtain are A, B, and C, and these are called the principal moments of inertia. Did you hit pause? Alright, so these are the principal moments of inertia, A, B, and C. And the three eigenvectors are the principal axis of inertia. And when we align our coordinate system with the principal axis, this is going to be our inertia matrix, A, B, C. Pretty neat and honestly pretty intuitive, isn't it? So now let's try to find our scalar moment of inertia with respect to this matrix. So let's consider let's consider a rigid body of n particles where the ith particle is at position Ri. Let A be a reference point and S be a unit vector, and let our axis of reference be defined as Q is equal to A plus lambda S, a simple vector equation. So the distance between Ri and the axis is going to be given by delta, which is equal to Ri minus A minus read. So when we solve this, we end up getting IL is equal to S dash IPS, where S dash is simply the matrix form of, S is simply the matrix form of our unit vector S, and S dash is just the transpose of that. And IP is our moment of inertia matrix. Thus, the moment of inertia about an axis parallel to S is given by this. Alright, now we're going to go into the fun part. Rocket dynamics. Rocket mechanics. Well, consider a rocket of mass m, whose mass changes at rate m dot, moving with velocity x dot. Now, notice that all of these are functions of time, because in a rocket, fuel is being expelled. Thus, the mass of a rocket is not constant. So, just a quick equation, differential equation we have for this rocket is mxi double dot is equal to m dot ci plus fi, where t is the time, m of t is the mass at time t, m dot is basically dm by dt, and it's the rate of the fuel that's being burnt, rate of burning of fuel. xi of t are the coordinates of the rocket at time t, and ci is the velocity of expelled gas with respect to the rocket. Fi is basically any applied force, gravity, aerodynamic forces, friction, whatever. So this is the equation which we have, and when we add m dot xi dot on both sides, this is what we get. Now, if we introduce a generalized coordinate system of n degrees of freedom, then we can define xi as a function of these degrees and t. Now, the kinetic energy of the rocket at time t is equal to this, and when we multiply by dou xi by dou q alpha, where q alpha is one of the degrees, is one of the dimensions, we end up getting this, which eventually simplifies to this, and this is the Lagrangian form for the generalized coordinates. If we take x to be equal to that, y equal to that, z equal to that, and we solve individually, we finally end up getting this as our equation. The Hamiltonian is pretty much the same. We calculate the Hamiltonian for the entire equation, and we arrive at the same equation. And thus, I conclude my report. I'd like to thank all the people who helped me out in this, and thank you.